Now let's focus our attention to reactor sizing, but now in terms of conversions instead of moles. We're going to start with the most easiest example, which is the batch reactor. On the figure on the left, this is a water treatment facility, and this batch reactor are very, very common in this industry. This is sequence batch reactor system. So while one reactor, the one on the right, is working, then the other one is shut down. Probably you can just unload it, and then the other one is being on working operation at the same time. So this is a way of maximizing the space available in the facility. This particular topic that we're going to be talking about will have some main goals. The first one is that we're going to go all over again the balance equation in terms now on conversion. This time I'm going to be skipping some steps and we're going to go to the conclusion, but the same analysis can be performed as we did before with mole balances. And the other thing that we're going to do is that we are going to size the reactors given the rate of reaction of the limiting reactant on one of the reactants as a function of conversion. Then we're going to see examples comparing CSTRs and PFRs. And we're going to be deciding the best arrangement for reactors in series to maximize conversion. And we're going to be calculating the overall conversion of reactors volumes for reactors arranged in series. So this is going to be a sequence of a couple of videos, the idea is that we mix them up. We mixed up different type of reactors and try to get or maximize conversion. So this section of the class is going to be really fun. So let's start with the definition of conversion. For conversion, we need to select reactant. Typically or most commonly is the limiting reactant as the basis of calculation. Remember that once you have the conversion for one reactant, you can use the stoichiometry pretty much to relate this conversion to other species in the chemical reaction. It is important that you choose the limiting reactant because technically is the reactant that will be completely consumed first after the reactant has been mixed, therefore provides more information about the reaction. Okay, so let's start with a general reaction. This reaction, we're gonna select A as our limiting reactant, and to have the chemical reaction defined as in terms of the chemical reactant, what we're gonna do is that we're gonna normalize the chemical reaction for 1 mole of the chemical reactant. So we're gonna have a chemical equation that will look like this. Okay, so that means that we can define conversion as capital X equals to the moles of A reacted over the moles of A fed into the system. Okay. This is an important quantity because it tells us information about how far the reaction proceeds to product. We can actually see that. We can also relate this to any other species in the chemical reaction. You can drop the subscript. You're going to see it that I just dropped the subscript because one of the assumptions when we develop this equation is that A is the limiting reactant. So once you know the limiting reactant, you can just define AX, right? Instead of using XA. I will use those terms, it will depend, right, on the type of problem that I'm solving. There are important things to consider when we have the conversion definition. One is that for irreversible reactions, where the equilibrium constant K, right, is really, really large, the maximum conversion that we can have, X maximum, equals to, or is close to, right, not always equal, is close to 1.0, 1.0. For a reversible reaction, X max conversion maximum equals to the X at equilibrium. Okay, we're gonna see examples for both, but it's important that we look at the chemical reaction, right, and the identity of that chemical reaction to kind of understand or guide us on what is the maximum amount of conversion we can have for that particular reaction. So for batch systems, we can define or we can assume, right, that the accumulation term is different than zero. That means that for the mass balance, this term is going to be important. So we need to define what is Na and see if we can find an expression, right, on the number of mole in terms of conversion. So we know that Na, right, can be defined as the moles entering initially in the reactor, not entering, initially in the reactor, minus whatever reacted of of species A. Okay, we can then take this term and try to get the derivative form, right? And we can see that with respect time and combining, we have remember that the sign is because we know that it's a reactant that is not being accumulated, it is being produced, and rearranging separating variables and integration provides the parameter for the batch reactor. Okay, this will be the time necessary to achieve a conversion of X in a batch reactor. Notice that the longer the reactants are left in the reactor, the greater the conversion will be. We can also represent this equation in a graphical form, right? If we graph Na initial moles of A, remember that this is also the initial concentration of A, we get a graph that looks something like this, kind of. Yeah, it looks something like that. And if I'm trying, right, this is X, try to get a specific conversion, trying to get to look at a specific conversion like this one, right? and then we look at the y-axis, right? Because this equation is in the form of an integral, we can see that the the area, right, under corresponds to t, or the time. So if we have data collected for that particular reactor, we can actually rearrange the parameters so they look like this type of graph, and we can graphically calculate the time of the reactor.